Hello and welcome back to my channel. Today is the part 2 of a few formula learned in childhood, Pascal Triangle and Pyramid and NMR Spectra. But before I start part 2, let me have a quick review of part 1 for better continuity. Okay, so we started with a few formula really learned in childhood, a plus b whole square or a plus b whole cube, and we are focused on these numbers 3 or 2 etc. In general a plus b whole to the power n, so we are focused on these numbers. Okay, so we interpreted these numbers in different angles. First we started with arrangement. So in the formula 3a square b, so this number 3 and a square b, how they are connected? It's through arrangement. How many ways you can arrange two a's and a single b, and that is of course 3, that we have explained in the part 1. And second question, that what is the general formula for the expansion coefficient a n minus k b k, and that also we know that it's a combination problem, that how many ways you can pick up k objects out of n. Say for example in this formula a cube b, so there are 4 objects, 3 a's and a single b, and how many ways you can pick up 3 a's or a single b out of 4 objects. So actually it is 4c1 or 4c3, and the answer is 4. And similarly here the question is how many ways you can pick up 2 objects out of 4, and that is 4c2, and the answer is 6. So this is how combination is connected to the expansion. Okay, and we know a very popular binomial expansion is exactly that, and this coefficient are nothing but n c k, where k goes from 0 through n, right? So this is binomial expansion. Now the last question we addressed is thumb rule, how we can by easy way remember these expansion coefficient values, right? And for that we got a beautiful triangle just from the formula and eliminating the letters and picking up only the numbers. So 1 1 2 1 1 3 3 1 and so on. So it looks like a triangle, and it's really called Pascal triangle. And how we can get that? The last line you can easily predict, because this 5 is 1 plus 4, this 10 is 4 plus 6 and so on. So that we have explained in details in the part 1, and this is the expansion for a plus b whole to the power 5, and similarly we can go for any a plus b whole to the power n. This is binomial expansion, and we have so far seen that how binomial expansion is connected, the coefficient of this expansion connected to arrangement problem, connected to combination problem, and how they can be represented beautifully by a sweet triangle, Pascal triangle. Okay, but the question, two more things actually are connected, and they are tossing the coin problems related to gambling, we can say, actually related to probability, the mathematical branch, and another is very important in analytical chemistry, and that is random errors. So all these 5 seemingly different aspects are connected through binomial expansion, that we have seen. But our question was, what about the proton magnetic resonance or nuclear magnetic resonance spectroscopy? How this can be connected to all these problems? That also we have discussed, taking an example of an organic molecule. Here you see 2 kinds of protons, blue and red. These 2 are equivalent, and this is slightly different because their electronic environment are different, because if you see that the carbon that the protons are attached to are having slightly different environment, electronic environment, right? So we can expect 2 peaks for these 2 different types of protons, a single peak for each, like this and that. So they are at different position, you see from the ppm value. Okay, now it's obvious that we are not getting a single peak, rather here we are getting a doublet, and here we are getting a triplet, and that is also quite obvious. I explained in the first part that it is not the electrical environment but the nuclear environment that actually affects. For example, when it is the signal of H A's, then HB is the neighboring proton, and it splits the single peak into a doublet. So a single nucleus splits into doublets, that is 1 goes to 2. But for HB signal, the lepton HB signal, the neighboring protons are 2, so it gives you 3 splitted signals, right, triplet. So that's the famous very popular to organic chemists, that n+1 rule, that is neighboring nuclei, if it is n, then the splitted number of spectra peak would be n+1. Fine, but what about the intensity ratio? Here it is clearly 50-50, that is 1:1, and here it is 1:2:1. And why this is so, that we have explained in depth in the first part, but the point is these ratios are nothing but the lines or rows of Pascal triangle. So 1, 1 the doublet, 1, 2, 1 the triplet, and similarly you can extend it to the quartet and so on, 1, 3, 3, 1, etc. So that is how this connected PMR to all other problems we have discussed, right? So binomial expansion, Pascal triangle, and PMR spectra all are interconnected, right? Now the question is that PMR, that is with proton whose spin value is half, but what about that we left in the first part? What about if the spin value is 1 or more than 1, right? That is the problem. So we can, to start with, we can, with our common sense, we can predict this first layer of this 3-layer problem, that binomial expansion. So is it going to be replaced by trinomial expansion? Probably yes, because per proton, as we know from quantum physics, its spin is half, and the number of spin states is 2i plus 1, that is 2 into half plus 1 is 2, and that is the value that we label with is minus I to plus I, that is here it is minus half to plus half, and we can represent it A by A and B, and n is the number of nuclei, so A plus B whole to the power n. That's how binomial expansion comes into the picture, right, in PMR. But what about if the spin is say for example deuterium, and spin is 1 and states is 2i plus 1, so it is 3, and what are the labeling values? Minus 1, 0, plus 1, because it's minus I to plus I. So we can represent by A, B, C, and n is the number of nuclei, so it is A plus B plus C whole to the power n. So that is quite understandable why trinomial expansion comes into the picture, as binomial expansion came in case of spin half. Okay, so the first layer is sorted out, but now the second layer, what about Pascal triangle? Is it the triangle can explain this pattern? Probably not. So what it is then? Is it some extension of Pascal triangle? And finally we will see the last layer, what about NMR spectra. So the second layer, Pascal something, extension of Pascal. So let us start with how we really get the numbers. So if it is A plus B plus C whole to the power 1, then we get just A, B, C, right? And we can present by a triangle A, B, C. You see the colors are different. Okay, that is quite obvious. Now A plus B plus C whole square, that means A plus B plus C multiplied by A plus B plus C. So A plus B plus C to the power 1, that means it is already A, B, C. Now it is being multiplied by A and then B and then C. So in terms of matrix approach, we can present it in this form, that A, B, C is already there for the A plus B plus C to the power 1 problem. Now we are adding n equal to 2 now, so another ABC comes into the picture, and we are multiplying A square, AB, AC, and so on. Thus we get 3 into 3, that is 3 by 3 matrix. And again you see the color, and you can easily understand that A square is 1s only, but AB comes AB and AB, so it is 2AB, and then B square is 1s, B square is 1s, and AC is again twice, BC is again twice, and C square once. So if you arrange in the triangle form, you will get a beautiful arrangement like this. Okay, fine. Now A plus B plus C to the power 3. So already you have got A plus B plus C whole square, this matrix 3 by 3 matrix. Now you are thinking of another a plus b plus c, so you are multiplying by another a plus b plus c. Now obviously the picture, the matrix that you have already got for a plus b plus c whole square, now it would be acted upon by a, by b, by c. So this same matrix when multiplied by a, so it gives you a square, that is a cube, then a square b, then a square c. You see, a cube, a square b, a square c, and so on. And then b, so ab, this a acting on ab, so it gives you a square b, then ab square and abc, and so on. So this is 1/3 of the job. The second part is that again you take the same matrix 3 by 3 for a plus b plus c whole square problem, and then you take b and let it work on this matrix. So it would give you another 3 by 3 matrix, and similarly for c. So a total of 3 by 3 matrices that you are getting. And again, if you want to arrange in triangular form, you can count, because the terms are colored differently. So a cube is red, a cube. Now a square b, if you count a square b, how many a square b are there in all these entries, then you will see it is 3. And if you count ABC, you see ABC 1, 2, 3, 4 and 5 and 6. So ABC is coming 6 times, right? So that is how we can easily arrange by means of some symmetry concept, and it is nothing but the binomial expansion for a plus b whole to the power a plus b plus c plus whole to the power 3. And so these are the numbers 3, 3, 3, 6, etc. here. And one interesting point is that if it is a plus b plus c, then it is 3 to the power 1. So 3 terms are there. If it is a plus b plus c whole square, that is 3 square, so 9 terms are here. And similarly here 3 to the power cube, 27 terms are here. So this 3 by 3 matrices, 3 into 9, 27 elements. That means if you add this expansion coefficients, those numbers, you will get 27. Here also we just get 27. Okay. Now we try to understand that is it Pascal triangle? No. Let us get it more clearly from another example. So this is the Pascal triangle. This is the number of rows, 0th row, 1st row, 2nd row, and so on. Interestingly, for a particular n, we are getting a triangle here for trinomial, but here for a particular n, we are getting a line. So line corresponds to triangle here, okay? And not only that, if you see it carefully and closely, then you will see this Pascal line is occurring in the 3 sides of the triangle, right? So you see 1, 2, 1 for n equal to 2. So a plus b plus whole square, in that formula, the terms arising in such a way that, and you have arranged in such a way in triangular form that 1, 2, 1, 1, 2, 1, 1, 2, 1. So the sides of the triangle is nothing but the Pascal line for a given n, okay? That's fine. But in case of triangle, Pascal triangle, when you take all the n together, 1 through n, then it gives a shape of a triangle. The lines now join to give a triangle. But here, the same question, you are getting line, you are getting a triangle for a particular n. Then when you take together all the n's, then what shape it would be? That is the question. Of course, it would be a pyramid. Sorry. Let us get one more example to make it more clear. A plus b plus c whole to the power 4. And by same way, if you get the expansion coefficient values and you arrange in this triangular form, you will see that this is the triangle. Okay. So we are getting bigger and bigger triangles at different n values, right? So if you join them together, if you try to draw a good picture, then it would look like a pyramid. And the first 5 layer of that pyramid would look like this. So you see 1 1 1, that first one 1 1 1, and then 1 2 1 1 2 1 1 2 1. So the three sides 1 2 1 1 2 1 and 1 2 1. The third one, here comes an extra 6. So again the lines are there, Pascal lines are there along the three sides of the triangle 1 3 3 1, but this extra 6 is coming here. Okay, and here the fifth layer, you see 1 4 6 4 1, that is the Pascal line. So 1 4 6 4 1, and similarly all other two sides 1 4 6 4 1. Okay, but here three new values are coming 12 12 12. So here we see also the 12 12 12. But how we can devise a thumb rule that if I am interested to have the next layer, then without doing anything else, how I can get the next layer and the values. So for that we have to make it clear that how this fifth layer coming from the information of the fourth layer. So nth layer we will make from the n minus 1th layer. How? Let us see. Yes. So 3 3 6. Again you see the total is 3 3 6 is 12, and this 12 is coming here. So 12 is coming here. Okay. And the 3 3 6 another. So we are considering exterior triangles. 6 3 3. Again it is 12. So this 12 is explicable, and here 3 3 6 another triangle. So another 12 is coming here. So that is how it's a kind of thumb rule that how we can make the next layer, the vacuum positions of the next layer from the previous layer information. Okay. So far so good. Now if I apply whatever you have learned, the thumb rule, for the next layer, the sixth layer. So it is going to be a triangle like this. Of course the sides are nothing but the Pascal lines 1 5 10 10 5 1. But how many vacant positions are there? So here again the exterior 1 2 3. So 3 exterior points are there, and 4 5 6. So by symmetry consideration we may expect that these 3 exterior points will have the same value and these 3 interior points will have the same value. Okay. Now what are those values, right? So as I have told that for the sixth layer you have to take help from the fifth layer. So let us see again the pyramid, 5 layer pyramid. So here you have to focus that what are the exterior triangles. Here the first one comes like 4 4 12, 4 4 12. This is the exterior triangle in the fifth layer. So the total is 4 plus 4 plus 12 is 20, and you are getting a 20 here. Okay, one exterior point. So now comes the next point here 20. So here again the next interior points is coming as 4 4 12 here 4 4 12, and similarly you will get another 20, and that comes from this 4 4 12. Okay, so that gives you the three values 20 20 20. Now we are left with these three values. So we have to search for again three such triangles, same triangles, and that is actually the interior one 12 12 6, that is 30. So the value 30 comes here. Now 12 12 6 is, this is the first one. The second one is again you see 12 12 6, and the third one is 12 12 6. So all are giving the value 30. So from this 12 12 6 you get the 30 here, here, and from this 12 12 6 you are getting another 30 here. Okay. So this is how we can say that we can construct by doing nothing almost, just by using the thumb rule, the next layer. You can try with, that will be a good exercise, that what would be the values for the seventh layer. Okay. Well, so as binomial expansion and Pascal triangle are having correspondence with each other, and that is also connected to the PMR spectra, these three layer problems we have seen in the first part. So that is well explicable for spin half. And then the question is spin 1, and that we have seen that trinomial expansion replaces binomial and Pascal pyramid replaces Pascal triangle. So up to the second layer we don't have any problem. But the next question now, the most important question is, what about the NMR spectra? Can NMR in general replace the PMR? That means spin 1 or greater than 1 replace the spin half? Okay. And the answer is unfortunately no. You see carefully that 1 is okay, 1 1 1 is okay, this pyramid is okay, but the next one is, this is the original spin 1 nuclei splitting ratio, right? That could be explained by physics. So there is no problem with this table, this triangle, but my question is whether this triangle is representable by Pascal pyramid, and that the answer is no, because you see here 1 2 3 2 1, but here you are getting 1 2 2 1 2 1. If you add the values, you will get the same one. So it is 3 square, that is 9. Here also if you sum up, that would give you 9. But the entries are different. Here it is 1 2 3 2 1, and here it is like this. So we see that it's a failure, right? It's a failure. That means trinomial expansion and Pascal pyramid, they are having their correspondence as usual, but that is not equivalent to NMR spectra. Now the big question, why, right? Why so? So let me explore a little bit more why. This is the spin 1 nuclei pattern, and we'll try to explain why this is not matching with the Pascal pyramid. And the problem lies actually this concept, multiplication versus addition. So what do I mean? It would be clear in a while. While we are doing the trinomial expansion, we are taking ABC and then ABC, and we are multiplying these values, A square, AB, AC, and so on. We are multiplying, right? But in case of spin, what we do, we have the spin -1, 0, +1, right? For trinomial case, and here again -1, 0, 1. So you have to add, you have to sum up to get the total spin. It is not -1 into -1, rather -1 plus -1, and that gives you -2. And that's how you see that this is the matrix where -2 comes once, but -1 comes twice, so 1 2, and then 0 comes 3 times, so it is 3, and then +1 comes 2 times, so it is 2, and 2 comes once, so it is 1. So that's how we get 1 2 3 2 1, not the other way as Pascal pyramid predicts. Okay, so this is the simplest example to understand why it is so. And now this is exactly the 1 2 3 2 1, this pattern. Now let us extend it further. So A B C cube, right? So we have already got A plus B plus C whole square, and then we will take one by one A, B, and C, that we have already seen. But here what we will be doing, we have seen that it's not a match for A plus B plus C. You see from Pascal pyramid, it gives you 1 3 3 3 6 3 1 3 3 1, and if you sum up these numbers, you will get 3 to the power 3, 27. But actual ratio, intensity ratio, is not exactly this one, but this one, 1 3 6 7 6 3 1, and that again adds you to 27, 3 to the power cube. Well, let us examine closely that how it comes. Well, we have already taken the A plus B plus C whole square case, that is this matrix we have already got. Now we are multiplying or taking another nuclei, you can say in this case, another nuclei, and that nucleus may come with either -1 or 0 or +1. So we have to treat separately this matrix with -1, and to get this matrix, suppose A, and then you have to treat the same matrix with 0 and the same matrix with +1. So that would give you the A plus B plus C whole cube case, and let us call it A, B, C. Okay. So how many terms are there? 3 matrices. So it is 27, no problem. But if you want to extend it further, and that would make it more clarified, what we will do next? We will take this A, which is an A plus B plus C whole to the power 3 situation, the first case. This is the second, this is the third. So we have to start with the first case, and then we have to choose the fourth nuclei, and that may come as -1 or 0 or +1. So we have to, in terms of matrix, we have to handle this matrix being operated by -1, 0 and +1. Operated means the way we have added, and we will get another 3 new matrices from A. Similarly from B and from C. So we will get 3 plus 3 plus 3. 9 3 by 3 matrices, right? So 9 into 9, a total of 81, that is 3 to the power 4 number of entries. Okay. So let us see, start one by one. Let us first take A. If you have counted already, then you will see that that gives you exactly 1 3 6 7 6 7 6 3 1. So that means this line, right? So already we have explained. Now we are extending it further, taking A, B, C separately and acting upon the A, B, C one by one by -1, 0 and +1. So let us see what happens. So we have taken A from the previous slide, and we have operated -1, 0 and +1 to give 3 new matrices D, E and F. Okay. Similarly, you have to take B and then do the same, and we will get another 3 matrices G, H and I. So 3 plus 3, 6 matrices, and now we have to take C matrix and -1, 0 and +1. That gives you another J, K, L 3 matrices. So if you now take together all the D, E, F, G, H, I and J, K, L, these 9 matrices having 81 entries, and for convenience the numbers are labeled with different colors, and you can give a pause and try to count that how many times this -4 comes, how many times -3 comes, and so on. They are different in color. So you have to look through all these 9 matrices, and then interestingly you will find that you are getting exactly 1 4 10 16 19 16 10 4 1, exactly the spin 1 A plus B plus C whole to the power 4 case. That means 4 nuclei case, and the ratio is this one. So if you count again, they are in different colors, consistent with these colors. So this 1 4 10 4 16 etc. is nothing but this particular line. Okay. So now we can say that Pascal pyramid and trinomial expansion they are connected, but not the NMR spectra. And for NMR spectra you have to do this, and why it's not connected, that also is explained. So I think up to this point it's very clear for you, but you can ask another question that okay, we have done for I equal to 1, but it's not a general case. So what if I equal to 3 by 2? What if I equal to 3 by 2, right? You can ask the question, of course, and then again by our common sense we can think of a tetranomial expansion, and then you have to search that is it a Pascal triangle or pyramid or something else, and then finally to answer the NMR in general. So if you are interested, I can come back with all these questions and answers in part 3 of this series, and till then thank you very much for bearing with me, for listening and watching this video. Thank you once again.